Sorry.
Keep forgetting.
All right. Okay. Test 1. Week from today. Held in class. And it's on material through section 13.8, which I'm going to start covering at the end of today and then all of Wednesday. So only stuff, now I might not get through the whole section, but only stuff that I cover is going to be on the test. So if there's a little bit left for next week, it won't be on the test, obviously. Okay, there's a practice test. And solution to the practice test on the lectures page of my site. I just updated it this morning. I added one more problem and also updated the solution. So I'd encourage you to look at that. However, I'm also going to use class time on Friday. I will be going over that and any other time I have left just to review in general. So the bottom line is there should be no surprises as to what sorts of things are going to be on the test. Now, one thing I want to point out about the practice test, because this comes up in every class where I give a practice test, because I do this so that there aren't surprises. That you have an idea of what sorts of things you should study. But all I can say is between the practice test and the real test, the problems will be of the same type, but certain particulars like functions and so forth will be different. It's not something where it's the exact same thing and I only change the numbers. There are more substantial differences than that, but at least you know what topics you need to study. Because sometimes it happens where on the real test, someone basically does a practice problem all over again. Don't do that. It's not going to end well for you. So this isn't a memorized fest. Well, no mathematics should be a memorized fest. Okay, so but at least I'll get far enough into this section. The problem I picked from this section is from the early part, not the end. So no matter how far we get or don't get on Wednesday, we should be okay. Does anyone have any questions about the test?
Will the test have the same number of problems as the practice test?
Yes, so the general framework is going to be exactly the same. Like, you'll see, oh, there's a problem on this section, this section, this section. The real test will have that too. So, yeah, there's 6 problems. So there's a chain rule problem, there's a directional derivative problem, there's a tangent plane problem, there's a problem, here's a function computed as partial derivatives. So all the kind of things you're asked to do in the practice test will be exactly the same on the real test. Again, just the particulars like what function is it, that could change. That still could make for a substantially different problem, but because I never want to have a situation where someone comes out of a test thinking, wow, they weren't expecting that to be on there. Well, now you know. So, okay. Any other questions about the test? Okay.
Are equation sheets allowed or?
No.
Okay.
Now, I may make a judgment call to put something on there, like I sometimes have in the past. But if I am going to do something like that, I'll let you know on Friday, and then I'll include it. I'll attach it to the practice test. I don't want someone's grade decided by how effective their cheat sheet is compared to someone else's cheat sheet. So if you're gonna have anything at all, it's gonna be the same for everybody. Okay. But yeah, sometimes like if it's the sort of thing that one can easily look up, easily Google, I might go ahead and put that on there because the whole point of the test is what can you accomplish when it comes to things that cannot simply be looked up. Okay. Any other test questions? All right, and this counts for 20% of your grade. No pressure.
No pressure.
Okay. All right. Now, let's see. Speaking of things being of various percentages of your grade, I do count attendance as 10% of a grade. I keep forgetting to take it. So today I am. All stragglers should be here by now. Okay. Now, we started on directional derivatives last time, and we don't have much left. So the only thing I have left in this section for today is about, I guess if I want to be informal, tangent stuff. And that covers both tangent lines and tangent planes. Depending on how many variables we're dealing with. Okay. So I'm going to start with tangent lines, and then we'll work our way up to tangent planes. So given a function, how can we describe a tangent line? Now, the equation is always going to look like this. Y is, we want a tangent line at a certain point on our curve, whatever curve we have. So you have a point x naught and then corresponding y value y naught that's on this curve, and this is our tangent line to it. That's not very well drawn, but you get the idea. And the way you describe it, first of all, what is the slope of a tangent line? What? Yeah, derivative. So that would be dy dx. And this notation here that's used now and then, a vertical bar, it's used to indicate that we're evaluating this at a certain point. We want dy dx at this point, x naught, y naught, times x minus x naught. So no matter how your curve is described, that is how you describe your tangent line. Y equals your y value plus your dy dx at that point times the change in x, x minus x naught. Basically, this is point slope form. But then how do you fill it in from there depends on how the curve is described. So if a curve is described explicitly, so you have y, that's the nicer case, y equals f of x, then you have y equals y naught, and then because you have f, you have y explicitly as a function of x, this is just f prime of x naught times x minus x naught. So that's a more straightforward case. But then what about the other case? So that right there, that's just cal 1. Implicitly, instead of y equals f of x, you have some other function, big F of xy equals 0. So this is a level curve that implicitly describes y as a function of x. And we do have a way of describing a tangent line in that case, because the way you get dy dx is, we have a formula for it, minus partial of big F with respect to x at x naught, y naught, over partial with respect to y at the same point. So that's our formula for dy dx. And that's times x minus x naught. Okay. And we used that before. For instance, we had an example involving tangent lines to a circle. So your big F was like x squared plus y squared minus 4 equals 0. So it's the exact same. The framework is exactly the same. The only difference is here we have a convenient way for getting dy dx. Here we have a little bit more work to do. But it's still dy dx that you want. Okay. But what's the limitation of this one? We can't always use it. When can we not use it? What could go wrong in computing that?
The partial.
Yeah. We must require that partial of f with respect to y be non-zero at that point. And okay, this came up in an example that we did. If it is 0, then what kind of tangent line might we have?
Vertical.
Yeah, vertical tangent line. But the thing is, there's still a tangent line. We just can't describe it using the usual formula, usual framework for equation of a line, like y equals mx plus b. A vertical line is x equals constant. So, so it would be nice if we had a way to describe a tangent line for this situation where our curve is described this way, with this kind of equation implicitly, that where it doesn't matter if partial big F with respect to y is 0 or not. Something we could use, as long as there's a well-defined tangent line, we have a way to describe it. And fortunately, there is a way to do that. This is still for the implicit case. There's nothing to talk about with the explicit case. That's done. So now we're prepared to go about this differently because we have directional derivatives that we can use. Because we could use the fact that on along this curve, the curve as described by this equation, big F is a constant because all points on this curve satisfy that big F at these points must be equal to 0. It's a constant function. When you have a constant function, its derivative is 0. So the directional derivative of big F is 0 if your direction u is in the direction of a curve. Now, so I'll draw a picture. Well, I could have used that one, but anyway. So here's my point, x naught, y naught. And this vector is, at this point, is heading in the direction of a curve. But what is that? That's the tangent vector. So, so what that means is, so this is my vector u, which is a unit tangent vector. And all parts of this description are important. It's a unit vector because directional derivatives require that we work with a unit vector for a formula to be correct. And it's a tangent vector because it's following a direction of the curve. Okay. So what we can say is, so the directional derivative of big F in this direction, which is the same as the gradient of F at this point, dot product with u. But now I can write out what that is. Gradient dot product with u is going to be partial with respect to x times u1, like the first component of u, plus partial with respect to y at this point, times u2, the second component of u, has to be 0. So this equation describes my tangent vector, this vector u that I'm seeking. So now I can use this to come up with an alternative equation for the tangent line. Because my tangent line equation should be like all the other ones, where we have a point xy on the tangent line, and we have some equation that it satisfies. Okay. So if I reproduce my picture, but now instead of just drawing the vector, I want to draw the tangent line, and the line has this direction, u, and this is my point x naught, y naught. So here we have some point xy that's on the tangent line. So what I can say is the vector from this point to this point, x minus x naught, y minus y naught, is must be parallel to the vector u. Okay. What we can also say is, but because the gradient of f at this point, dot product of u is equal to 0. When two vectors have a dot product of 0, this came up on Friday, what must be true of those two vectors? Well, how do they relate to each other? They're perpendicular or orthogonal. So we have gradient of f at this point perpendicular to u, and these two vectors are parallel. So the gradient of f must be perpendicular to this vector, the vector from our point of tangency to our point on the line. Okay. So in fact, the gradient could very well be pointing in this direction, or it could be pointing the opposite direction. The point is, it's along that perpendicular. Okay. So the gradient of f dot product with x minus x naught, y minus y naught must be 0. So if I write out what the dot product is, now we have an equation of the tangent line. So partial of f with respect to x times x minus x naught plus partial with respect to y times y minus y naught. That must be equal to 0. So this is how I can write the equation of a tangent line in the case where your curve is implicitly described. And notice there's no division going on here. It doesn't matter whether fy is 0 or not. This is something that always works. Okay. So if you have an implicitly described function that describes your curve, that's the best way to get the equation of a tangent line. Now, if we compare this equation right here with the other one I wrote earlier that had this restriction over here. So if we compare what's boxed, how can we get that one from this one algebraically? Why is it that the two are basically equivalent? manipulation could I do to this equation to get that one?
When you subtract the y naught over and then multiply the partial of f over.
Um,
Divide rate.
Yeah, that's it. Just multiply through by Fy. And then, yeah, you do a little rearranging. But yeah, and it makes sense that the equations really are equivalent because the tangent line is unique. So we really are saying the same thing. It's just that because this is written in a way that doesn't have division, we don't have to worry about whether Fy is 0 or not. Whereas in that form, you do. So here we don't necessarily have a dy dx. So this is written in, like, I believe they call it like a standard form of the equation of a line. So it's not point slope, it's not slope intercept. There's no slope you can just pick out. You'd have to solve for it. So as long as it's not a vertical line, you could solve for it. Okay. All right. So what we have here is when we have a curve like this described implicitly, in other words, it's described as the level curve of some function, big F of x, y equals 0, then this is the equation of our tangent line. Okay. Now, the same idea is true of a tangent plane. So now if you have a surface big F of x, y, z equals 0. So that implicitly describes z as a function of x and y. Now what we had before, we have was z minus z naught is equal to partial of z with respect to x times x minus x naught plus partial of z with respect to y minus y naught. And we had formulas for dz dx and dz dy. This was minus fx over fz evaluated at the point of tangency, x naught, y naught, z naught. And this was minus fy over fz, again evaluated at x naught, y naught, z naught, your point of tangency. And we had the requirements that partial f with respect to z was not 0. So it's the exact same dilemma. And we can resolve it in the exact same way. Multiply through by fz. So we have partial of f with respect to x at this point, x minus x naught, plus partial with respect to y at this point, times y minus y naught, plus partial of f with respect to z, z minus z naught, must equal 0. Okay, so geometrically, what's happening is, here's your surface, here's your point of tangency, here is your tangent plane. So I could have any vector, like my vector u, could be sitting within that plane, and the gradient is normal to that plane. So within the surface, big F is a constant function. It's always equal to 0. So we have gradient of f dot u of gradient of f at this point dot u is equal to 0. Whenever u is a vector contained within the tangent plane. So for a tangent line, we only had one direction to choose from. We could go forward or backward along this line, and that's it. In the case of a tangent plane, you could choose it along infinitely many directions contained within this plane, but the same equation still holds. Okay. All right. All right. So what I've boxed here, these are formulas you should know, and you should see how they relate to one another. They're very similar. Here we have what's going on when you have a curve described by a function of 2 variables, or a surface described by a function of 3 variables. But the formulas are very similar, but you have some dot product of a gradient, fx, fy in this case, or fx, fy, fz in this case, dot product with a vector within your tangent line or tangent plane. X minus x naught, y minus y naught, z minus z naught. All right. So what I'll do now is I'll step through an example involving, the more interesting of these cases, a tangent plane. So you can see how to get the equation of whatever tangent stuff is required. And yeah, I could have just taken the old formulas and multiplied through by fy or fz, but that wouldn't give you any idea geometrically of what's going on, or where these tangent line or tangent plane equations come from. Okay, so I'm going to have a function of 3 variables. Is x squared plus y squared plus z squared minus 2x minus 4y minus 4. And we set this equal to 0, so that describes a surface. So implicitly it describes z as a function of x and y. Now, what kind of a shape do you think this equation would describe? What three-dimensional shape? It's a sphere. Because you have equal coefficients of x squared, y squared, and z squared. Now, what would you have to do algebraically to figure out the particulars of the sphere, like its center and radius? Because it's not obvious right out just reading off the equation, but how would you go about doing that algebraically? You can complete the square. So I have x squared minus 2x. So if you have like x squared minus 2x plus 1, you can condense that to x minus 1 squared. I won't go through all the algebra here, but if you were to complete the square in just x and y, you don't need to do it in z. The center is at x equals 1, y equals 2. It's taken from half these coefficients here. And z is equal to 0. And the radius is 3. Okay. So completing a square in x and y would lead you to that. So this is equivalent to x minus 1 squared plus y minus 2 squared plus z squared is equal to 9. All right. So I'm going to choose a point that is on this sphere. X is 3, y is 3, and z is 2. Okay. So the problem is, what is the equation of a tangent plane at this point? So to get that, we just use a formula that I've boxed over here, this one. So we need the gradient of f at this point. So that's going to be fx at 3, 3, 2, fy, 3, 3, 2, and fz at 3, 3, 2. Okay. What are my partial derivatives with respect to x, y, and z?
X you get x squared, I mean, 2x minus 2,
Okay, in respect to y
2y minus 4,
and z,
2z.
yeah, just 2z. Okay, and we're evaluating this at a point 3, 3, 2. So what would that give me?
6 minus 2, 4, 2, 4.
Yeah, so that is what the gradient is at
What?
that.
What is that, it's got fx 3, 3, 2, what is that behind your 2 up there?
Oh, this?
No, down here at the fx. Right, no, on the same line.
Okay.
2, what's that behind the 2?
Oh, it's a parenthesis.
Oh, sorry.
Okay. All right. So this is my gradient at the point of tangency. So that means, well, now we can wrap up. So equation of a tangent plane is, well, I'll write a dot product form first. So 4, 2, 4, so this is a gradient. Dot product, so it's orthogonal to x minus x naught, y minus y naught, z minus z naught is equal to 0. But for x naught, y naught, z naught, we're filling in our point of tangency. So we get 4 times x minus 3. So that's the first term. What's the next term? So we're carrying out this dot product. You multiply corresponding components and add them up.
2 times y.
Mm-hmm.
4.
Yeah, z minus 2. And don't forget, 'cause some people did forget this on the test, last time I taught this, all that is set equal to 0. So that is your final answer. That is the equation of the tangent plane. So any questions about how we get the equation of a tangent plane? Now keep in mind, it's only for a case where your surface is described implicitly. Big F of x, y, z is equal to 0. If it's described explicitly, z is equal to a function of x and y, then use a formula I wrote way back at the beginning of class. So the explicit form, z equals f of x, y, is z minus z naught is equal to partial of z with respect to x, or fx, times x minus x naught plus fy, y minus y naught. So it's very important to pay attention to how is your surface described, or in the case of 2 dimensions, how's your curve described. That tells you which kind of equation you use. All right. Now, questions? Now, one other thing we can pick up from this is what's called a normal line. So, if I draw a situation here, here's your tangent plane, and then you have a line that passes through the point of tangency, and it is perpendicular to the tangent plane, or it's the we're going to call from calculus 3, the normal to the plane. And given what we've just computed, the equation of a normal line is very easy to write down by proceeding using parametric equations, which also would have come up in Cal 3. So you say x is equal to x naught plus t times fx at that point. And then same thing for y. T is your parameter that describes any point along the line. And then z is equal to z naught plus t fz at that same point. So in this example, we have x, y, z on the left side. On the right side, just fill in your point of tangency, 3, 3, 2. And then the coefficients of t you get from your gradient. So we'd have 4t, 2t, 4t in this case. So everything you need to get the tangent plane also gives you the parametric equations of the normal line. I think I might have thrown it in some of the homework problems for this section. It's not going to be in the test. So there will be a problem from the test on, here's a function described explicitly or implicitly. What is the equation of the tangent line or tangent plane? So everything I've been talking about today. Okay. So questions on this example? Well, it actually concludes this section. We have one more section that's covered on the test, max and min. I will start that during these last 10 minutes. We'll pick up with that again on Wednesday. Now, in Calculus 1, you learned how to compute the max and min of functions. Today we're going to talk about local max and local min. And similar ideas apply in multivariable. To keep things simple, we're going to focus on functions of two variables. So I'm going to make a little chart here of criteria. What do you test for to find out if a function has a local max or local min? So this gets into section 13.8. Okay, so first, quick review from Calculus 1. So you have some function y equals f of x. You want to find out where it has a local maximum or local minimum. So something like this. Like this is a local maximum. This also is a local maximum. It's not the absolute maximum, but it's a maximum of nearby points. This is a local min. And so forth. Okay. So what do you recall, hopefully, some of you, doing in Calculus 1 to find local maximum? Given your function, what's the first thing you would do?
Take a derivative.
Take a derivative.
Get your critical points.
Yeah, so your critical points. Alright, so you take the derivative, what do you do with the derivative?
Set it equal to 0.
Set it equal to 0. Okay, and then there's different things you can do to determine once you have a critical point, whether it was a max or a min or neither one. Let's focus on one way in particular, the second derivative test. So if you found a critical point or critical number where first derivative is 0, and then you check the second derivative, I'll use x naught to indicate the point where this happens. If the second derivative at that point is positive, what would that signify?
Max.
You'd think so, but no, it's a min. I know. No, because it's a situation like this. Here, the second derivative is positive because it's concave up. So you have f prime equals 0, so that's a min. And therefore, if it's negative, it is a, yeah, well, it's the only possibility left, isn't there? So you have a situation like this where it's concave down. Okay, and if it is equal to 0, it's actually inconclusive. you may have like an inflection point. Like, you know, is there an actual, really depends on whether it's a sign change in the first derivative. That tells you if it's a max or min. That's really the if and only if of it. Okay, so that's what you had to do in one dimension. So I'll just write the last case, if it equals 0, it could be a max or min, you just don't know. You have to try something else. Okay, so what happens in the multivariable case? I don't have much time, but I'll give you the general idea. These are things to know for a test. And we'll do examples on Wednesday. So I'll focus on z equals f of xy, because really on a test, it's only practical to look at this from a function of 2 variables, although I can tell you how to do it in more variables. So your critical points, if I were to describe, like visually, here's a case of a function, and I probably should be shading or something, but think of this as a surface, where here we have a local maximum. And the idea is, if you were to take any 2-dimensional slice and see what's happening like along any curve and pass through this point, in any direction, there should be a horizontal tangent. There should be a situation like this, no matter which slice you take. So in other words, the directional derivative should be 0 no matter what direction you're taking. But the only way to make sure of that is that the gradient of f must be the 0 vector. In other words, both partial derivatives, or all partial derivatives, however many of you have, all of them must be equal to 0 simultaneously at that point. So really, you basically have a system of 2 equations to solve, because both must be 0. Because otherwise, you have a situation if only one of them is 0. Yeah, you may have a max or min along one slice, but not within another. Okay, so but you can see the similarity. So whatever derivative, first derivatives you have must be 0. Okay. Now there is a second derivative test. I'm going to define some notation here. It's called the Hessian of f. And what it is it's a matrix of all the second partial derivatives. fxx, fxy, fyx, fyy. You just arrange them like this. So this is used to classify critical points as either a max or min or other things. So what's the counterpart to this? Second derivative in one dimension is 0, is positive, and therefore it's a local minimum. So the Hessian is what is called positive definite. But that's a term, that's a linear algebra term, which I'm not going to get into. So what I'm going to do is make things easy for you and explain what does this actually mean in this case of 2 variables. It means that this expression, which I'll call D, is fxx, fyy minus fxy squared. Has to be strictly positive. You might recognize this as the determinant of the Hessian matrix. Must be positive. And there's more to it. Basically, if you check that the ones along the diagonal, fxx and fyy, must also be strictly positive. So this is for a minimum. Okay. Now, So basically that's your second derivative test for a function of two variables. To have a local max, and all this is local. Talk about absolute maxes and mins on Wednesday. A local max is similar. The same quantity d must still be positive, but your diagonal derivatives fxx, fyy must both be negative. So that's the counterpart to this case, where second derivative is negative for a local max. And then the other possibilities, which are more unique to multivariable, if the same expression d, which is fxx, fyy minus fxy squared, is negative, that is called a saddle point. So that's something usually, we don't have anything like this in single variable. What that means is, you have a case where a function has a local maximum along one slice and a local minimum in another. So like these curves can be perpendicular to each other. So you think of is a local max along these directions and a local min along these directions. It gives the graph of the surface the appearance of a saddle, and that's why they call it a saddle point. So it's an unusual case of having neither a max nor a min. And the only possibility left is, so this is case 1, case 2, case 3. The only possibility left, case 4, is where this expression is equal to 0. In that case, we don't know anything. It's like when the second derivative is 0. In the one-dimensional case, it's inconclusive. We'd have to look at other things to determine if there's a max or a min or a saddle point or none of the above. Okay, so like I said, I'll do examples on Wednesday, but the idea is we'll see how we step through this. We're given a function, we look at its partial derivative, see if we're both 0, and then we perform this second derivative test. We look at this expression d and try to classify its critical points, however many of them we have. Are they local maxes, local mins, are they saddle points, or we don't know. So, and also in Calculus 1, sometimes you had to interval, you had to check the endpoints. There's a counterpart to that in multivariable also. We'll take a look at that on Wednesday, but it won't be on the test. Okay, you can scram now. Whoops.
I think I figured out that.